everyone. Welcome back to the OChem 2 weekly review. This week we're going to go over chapter 22 and 20, basically 22, 20, 21, and 22. So it's kind of out of order since that's how they structured it this semester. So we're going to start off with 22, which is your enols and enolates. All right, so give me 1 second. So there's a couple of different reactions you have to know for this chapter. So let me draw the first reaction. So let's say you have a ketone that looks like that. And then it's being reacted with LDA, which you guys should be familiar with. It's a very bulky base from, last semester, used in a elimination sense. But in this regard, we are using it as a deprotonator. Negative LDA can be paired with either cold or hot temperature. So let's say we are undergoing cold temperatures. So for example, negative 78 degrees. And then I'm going to draw the same thing. So same starting compound, same reagent, but this time it's going to be heat. So it could be the heat symbol, which is the little triangle, or they could just give you like positive 78, for example. Okay. Of course, it doesn't have to be these specific degree values. Just know that there's a cold and there's a hot version. Okay. So if it's cold, it's going to be kinetic. And if it's hot, it's going to be thermo. Okay? And a simple way to remember kinetic is cold is that kinetic also has the word, starts with the letter K, and that sounds like the word cold. Now I know it starts with the C, but imagine it's with the K. Okay? So if it's kinetic, it's going to attack, it's going to deprotonate the less substituted hydrogen. Okay, so that means we are placing a negative charge on the right side, just like that. And then if it's thermo, we are going to attack the most substituted carbon. Okay. And then now you have a negative charge, which can now do substitution, because now we have a good nucleophile with negative charge that can attack a carbocation with electrophile with the leaving group. Okay. So these are your enolate ions, because whenever we form a charge right here, that's what a ion is. Okay. And then a quick side lesson is to go from a ketone to a enol. The specific word is called tautomerization. Okay. Basically, you have two different forms of the same thing. And to switch back and forth, we call it tautomerization. So let me write everything. So this is ketone, enol, and then in between is called tautomerize. Okay. So it tautomerizes from a ketone to an enol, and then from an enol it can go back into a ketone by tautomerizing. And the reason why it's called enol, a good way to remember is the En, remember that's your double bond alkene, and then the Ol is of course your alcohol. And then ketone, the One is the nomenclature for ketones. Okay. All right, next we're going to talk about aldols. Just a quick headliner. This is chapter 22. These are your enolate ions. Okay, now we're going to talk about aldol. So the way you remember what an aldol reaction is when there is no good leaving group, so it attacks itself. Okay, and I'll show you what I mean. We're going to use the same exact starting compound, this ketone with 2 extra carbons or 1 extra carbon on the left, and then the reagent we're going to use is NaOH. Okay, a very common aldol reagent. You can also use NaOCH3. Basically any strong basic, no pun intended. So even LTA would work. Okay, so I'm going to use heat. So because it's heat, it's going to form a negative charge right here. And there's actually not going to be any, this is the entire problem. So there's no electrophile, so you have to make your own electrophile by reacting with its own self. Okay, so if we flip it over and reverse it, we should get something like this. Okay, and let me switch colors. So this negative charge will attack this carbonyl because, as you guys know, there is always a partial positive and a partial positive. Partial positive and a partial negative for any carbonyl. Okay, because of the dipole polarity moment. Okay. So when all is said and done, and when it attacks, obviously it's going to form a new bond, but this already has 4 bonds, so this extra carbonyl double bond is going to add on to oxygen, which forms a negative charge, and that negative charge eventually turns into hydrogen. So at the end of the day, we should get a tertiary alcohol, and I am going to draw that. Okay, so there's your original compound. Here's your second compound. Okay. One sec. Okay, so there you have it. That should be the end result of your aldol reaction, and almost all aldol reactions will function this way. Of course, an additional step after this that you might encounter is going to be dehydration of water. So we're going to lose this OH as well as a adjacent hydrogen to form a double bond in between after eliminating those 2 structures or compounds. Okay. Next, we have something called Claisen Ester condensation. Okay. So this one is relatively similar, except this time the electrophile and nucleophile are on the same molecule. You may know, you may recognize this type of interaction back in OCHEM 1, known as intermolecular reaction, which is exactly what this is. So I'm going to draw the structure. 2, 3, and you have an ester here, your R group. Here's your 2 carbonyls, one at each ends. So you have a ketone on one side and an ester on the other side. And then your reaction is going to be NaOH. Okay, with heat. So you're going to go for the more substituted secondary carbon rather than the methyl groups on the outside. And of course, you always want to do the alpha ones because of resonance and stability. So we are going to deprotonate. So a good question is, which alpha carbon do I do? Do I do the ketone or do I do the ester? Okay, and that is a great question. So you have to refer to your carbonyl reactivity. Okay, ketone is going to be more reactive because it has more electron donating groups. At least, yeah. And esters are going to be less reactive. But yeah, long story short, between ketone and ester, you're going to deprotonate right here. And then it's going to attack the other carbonyl. Of course, whenever we attack a carbonyl, if it has a good leaving group, such as this OCH3, it's going to kick it out. But we're still going to form a ring, except instead of the ester, we're going to have a ketone. So when all is done and said, what you want to do is you want to count your carbons. So let me do that. So 1, 2, 3, 4, 5, and 6. Okay. So always make sure you're counting your carbons. I know that may seem like something you would do in the first week of Organic Chemistry 1, but even in the final unit or second to the last unit of OCHEM 2, you're still going to have to use those basic rules. Okay, so 6 obviously means a hexagon. Okay, and on the 6th carbon we have a ketone, and on the first carbon we have another ketone, but it's on the outside. Okay, so you should have a cyclohexagon with 2 ketones, one in the ring, one on the outside, and I was able to do this because I counted my carbons and I recognized what my reagent meant and which one takes priority. Okay. All right. So the next thing I want to talk about is something called Alonic ester synthesis, also known as decarboxylation. Okay. So here let's say we have an ester. Okay, and we also have another ester. And a methyl right there. And I'm gonna zoom in. Okay. And the reagents that you're reacting with are gonna be H plus and H2O. So it's gonna be acidic water as well as heat. Okay. So this is kind of something you learn in chapter 20 and 21 with carboxylic acids and their derivatives. But basically, anytime you have a carboxylic acid derivative, which is what an ester is, and you react it with acidic water, such as H plus H2O, it will transform one of these acidic or one of these carboxylic acid derivatives into carboxylic acid. So that's step number one, and I'm going to draw that before I get to step number two. So I'm going to pick the right one to undergo this reaction. So instead of an ester, we have a carboxylic acid. Okay. Now, if you refer back to the name of this reaction, it's called decarboxylation. And that always means we're getting rid of the carboxylic acid. Okay. And that is where step number two comes in. Heat will always cleave this off, and this leaves as CO2. So you might recognize this terminology. So just be careful of that. Also, something I actually made a mistake is this ester actually also becomes a carboxylic acid, not just the right side. So we have two carboxylic acids, but only one side gets decarboxylated. Okay, so at the end of the day, you have alcohol, or rather carboxylic acid, and then plus CO2. Okay. Now, of course, something to think about is what if you have other groups instead of carboxylic acid or ester groups? For example, let's say this was a aldehyde, which is what is going to be more common. It's more common to have two different types of carbonyls. So you can, because they want to test your knowledge on reactivity of carbonyls. So if you have an aldehyde here and a ester here, the aldehyde is going to be more reactive, and the acidic water is going to transform the ester group rather than the aldehyde. And then, of course, the carboxylic acid gets cleaved, and then you're just left with the aldehyde as well as CO2 being released. So similar to this, but imagine a aldehyde. Okay. All right. So now we're gonna go into chapter 20 and 21, which is your carboxylic acid and its derivatives. So I'm gonna zoom out, let you pause or take a screenshot and copy all this down into your notes because I'm going to erase it in 3, 2, 1. So we're going to draw kind of a big chart, and And because it's the chapter of carboxylic acids, we're going to draw a big one right here. And when I mean chart, I mean a tree branch type of model. So we're going to have one right there, one right here, one right here, and then one right here. So I'm going to give you guys 4 reagents. So try to see if you could understand what they do. So the first one is going to be SOCl2. And the rest of them I actually have to draw. So the second one is going to be carboxylic acid. So reacting with itself. Third one is going to be methanol. So methyl with alcohol. And the last one is going to be amine, which is a R group attached to a NH2. So this is going to be a primary amine. Okay. So the first one, SOCl2, hopefully you guys should know this. It will turn carboxylic acid into acid chloride. So replace the alcohol with chlorine. If you react a carboxylic acid with another carboxylic acid, it will turn that into a compound called anhydride. Basically, you have 2 carbonyls with an oxygen molecule in between. Next, we have methanol. It will create a ester. So OCH3 is being formed instead of OH. And then last but not least, we will create a amide. So 1 hydrogen leaves, and we're left with the N and the R and the carbonyl. And in fact, if you notice, 1 hydrogen leaves in all of these structures, except maybe that one. But basically, this 1H and the alcohol leave as water. And as you know, water is a good leaving group. Alcohol is not. So we need that extra hydrogen in these structures to provide that stability so it can leave properly, and then we form a negative charge, and then it's a nucleophile attack. So if you think about it in OChem 2, a lot of nucleophilicity and electrophile attacking mechanism comes back into play. So if you're having trouble with that, I would go back and review Unit 2 of OChem 1, whatever the unit was for the 4 mechanisms, SN1, SN2, E1, E2, because that is important. Okay, and then same here, this H and OH leave, you're left with OCH3, and that's what you have right here. And then 1H leaves along with OH, it leaves us water. 1H is still left behind along with the R, so you have amide. Okay, so again, the first one is acid chloride, and one is called anhydride. This one is ester, and then amide. Okay, so these are your carboxylic acid derivatives because they derive from your carboxylic acid. Okay, so far so good, right? So nothing too fancy, except now we're going to go have a little bit more interconnections. in further reactions. So an acid chloride can actually become anhydride if you react it with carboxylic acid. Okay? So before, OH was not a good leaving group, so we needed the extra H to form water, but chlorine is actually a very good leaving group, so we don't need the extra H. But this time, instead of forming water, it forms hydrochloric acid, which also works. So if you take this and put it right here, it should create anhydride. Okay? Let's see. Yeah, okay. So acid chloride can reduce into aldehyde through a soft reduction, not as great as LAH, but something weaker than that is, and I'll type it out, it's called LAH, parentheses, OT mu, parentheses, 3. Okay, so terbutyl or terbutoxide. The O is obviously an oxygen, T is the terbutyl, Tbu, and then 3. Okay, so with this combination, you can reduce acid chloride into aldehyde. If you don't want to use LAH, which will reduce it completely. And then going back into the carboxylic acid, so I'm going to redraw this over here. All of these, acid chloride, anhydride, ester, and amide, all have the same mechanism or reagent. And we already talked about this, and we've seen it on the previous whiteboard. It's going to be your acidic water, so H plus slash H2O. Okay. Again, we need OH to react. So where the H that was lost here is going to be the extra H from H2O. This H leaves to provide the methanol, the primary amine, the carboxylic acid, the HCl. So that all goes away, and then you're left with a electrophile or nucleophile here with the O minus or OH minus, and that will attack each of these to create that carboxylic acid again. All right, so that should be majority of it, but there's one other thing that we can do from amine actually, and if we use POCl3, we can create a compound that looks like this. And by compound, I mean cyanide. Okay, and then cyanide will also do the same thing by turning back into alcohol or carboxylic acid through acidic water. Okay. All right. Well, there you have it. These are your carboxylic acid derivatives and its reactions. This is a very basic outline of that should help you with the rest of those reactions. There are a few other smaller reactions, but I will refer to your lecture on those the smaller ones. And this is a broader sense to understand the trajectory of carboxylic acid and how these derivatives work. Okay? All right, well, there you have it. I will see you guys next week. Let's see what you guys are doing. So you have your exam on April 7th. So that's not this week, obviously, not this Wednesday, but the Wednesday after. Okay, so next week we're gonna go into, we're just gonna do some practice problems, and I'll give you guys more reactions to learn and to understand, and then hopefully you'll spend the next 2 days following that preparing for the exam. Definitely, start studying this week and start going through your lecture slides and going through each reaction because there is quite a lot, and because it's in different order. It starts with 22 and then jumps back to 20 and 21, and then of course 18 and 19 before spring break, or spring break and the winter break, snowstorm thingy. But yeah, if you guys have any questions, let me know. I will be back next week on Monday for the weekly review, and hope you guys have a great week. Good luck.